Alright, so we are about to get rid of Cygnus. This vehicle is a cargo vehicle that has been our dumpster for the past many months. It's currently full of trash. We're here in Node 1. This is looking down toward Earth. This is the Node 1 Nadir hatch. And below this hatch, which is the Cygnus hatch, is the Cygnus vehicle full of trash. And we've just closed out everything in the vestibule here. The vestibule is the space between the Cygnus hatch and what will be the Node 1 Nadir hatch. And so soon, these two little seal beads here will be the only things keeping the pressure inside the space station. And right here where my hand is will be the vacuum of space. The Cygnus vehicle is still powered. We were powering it off the space station, but now the robotic arm has already grappled it. And the space station robotic arm is actually providing the power to Cygnus now. And so after we close the Node 1 Nadir hatch, our common berthing mechanism will have ground controllers actually unbolt the Cygnus vehicle from the space station, and then the robotic arm will unberth it and move it away from the space station to a point where it can be released, and then it's going to fly itself back downhill and have a destructive re-entry back into Earth's atmosphere. And we are ready to close up.
I do that.
All right, filling hatch, stowage latch button push, stowage latch handle pull down, hatch pull, push close, arrows aligned. Latch. We are latched. Excellent. Stow the handle. Crank handle stowed. That's it. Okay, welcome to the airlock aboard the International Space Station. This is where we do all things spacewalking. And it's currently May 31st, and we're getting ready for an EVA, a spacewalk, on June 9th. We're just kicking off what we call the Road 2. That's all the activities leading up to our EVA, getting all the equipment and suits ready. And today we're doing something called a loop scrub. So inside the spacesuits, there are water tanks and water loops. And water serves two purposes in the spacesuits. Number one, it's our cooling fluid. It's the working fluid for keeping us cool as crew members. We wear these garments called LCVGs, the Liquid Cooling and Ventilation Garment. And inside here, there are all sorts of tiny little tubes filled with water that's constantly circulating and keeping us cool. The other thing that water does is it feeds the sublimator. So the sublimator at vacuum is sublimating water away, and that's what allows the heat exchanger to reject heat out of the system. And so that's a constant sort of, water is actually a consumable in the spacesuit. We're constantly losing a little bit of water to the sublimator. So we have a primary and a reserve water tank, and that's one of the consumables that we track during the EVA. We're actually able to top off our consumables using these umbilicals, the service and cooling umbilicals. These are connected to the suits while we're in the airlock, and we can top off our battery state of charge, top off our oxygen, and top off our water before we leave. So we'll disconnect these right before we leave the airlock. And today, the suits are actually powered on, the fans are running, and we're pumping water through the system. And we've got this complicated assembly of tubes and filters, and this is what we're using right now to scrub those water loops on both suits. We also have a conductivity analyzer up here, so we're paying attention to the conductivity of the water and making sure we have high quality water before we take these suits out to space. In here, in the airlock, this is the equipment lock section that we're in now. This is where we get everything ready. And then behind me, it's filled with some stowage right now, but eventually this crew lock section is where we go and we pump the crew lock down to vacuum, and then there's a hatch in the floor that leads all the way out to space. Okay, today is June 14th, and Steve and I are doing our final preparations before heading out on a spacewalk tomorrow to install our second set of IROSA solar arrays on the space station. I thought I'd quickly show how we drink water in the suit. This is our DIDB, or DIDB, our disposable in-suit drink bag. Holds just under a liter of water, and I've just filled mine up and ready to put it in my suit for tomorrow. Now, one of the things that happens with water up here, everything floats, it's weightless, and so there are some air bubbles in here, some pretty large ones, and I'd like to minimize the volume that this drink bag takes up in front of me in the suit. So you can't just hold it here and let the water fall to the bottom and suck the air bubble out. But one of the tricks we use is spinning things. So we get some centrifugal force going and get the water all the way to the outside. And then it really helps, you have to be very gentle. So as you slow it down, we had centrifugal force holding the water out to the edge, and then if we slowly let the rotation stop, the surface tension of the water takes over as the dominant force and holds all the water where it is, which right now is in the bottom of the bag. And we get a nice air bubble up at the top that I am going to suck out. Now, surface tension took over a little bit there, so I'll do a second round. Or surface tension moved the water up to the inlet. Get a little aggressive here and get it out to the outsides. And then slow it down nice and carefully. And that is almost all of the air out of the drink bag. Next thing I'll do is put this in the suit. All right, it's June 14th, we're getting ready for an EVA tomorrow. A few days ago when I did my first EVA, I felt like my suit was just a little bit short. I had a lot of pressure on my shoulders, so we're making a small tweak for tomorrow. I'm gonna extend where the crotch and the feet of the suit land to just alleviate a little bit of that shoulder pressure. So I thought I'd show how we can resize components of the suit. One of the ways we have is these things called sizing rings. Down here you see one installed between my leg and my boot. There's just this ring of metal, and this is simply to extend the length from my knee to my foot. I have some of those on my arms as well. The other thing we have are these cam buckles, and they allow us to make fine-tuned adjustments to the legs, the arms, and also to the torso itself. So what I'm doing, I've already done my right side, and I'm coming in here now to do the left side. This is the actual change to my sizing that we're making for tomorrow's EVA. Currently, I'm in long short on this restraint strap that holds the distance of the sort of pants from the top of the suit. This is the actual restraint fabric, and this cam here is holding this restraint strap a little bit short. What we're going to do is pull this pin and allow the restraint strap to go to the long position instead of the short position. So this is now sitting about an inch lower than it was before. And that's it. I've already done that on the right side, just did it on the left side. We're now in long. So that's as long as we can go. And we'll zip it back up. We'll be ready to go. All right, it's almost time for Evening DPC, which is the daily planning conference. We have two of these a day, once in the morning, once in the evening. The crew gathers and we talk to flight control teams around the world. By tradition, the ISS commander kicks it off. So tonight, Sergei Prokopiev will kick off the conference on Space to Ground 1, and then Houston will take over and we'll see if they have anything to tell us this evening.
Houston, Council, Phoenix, Cuba, Moscow, Expedition 69 is ready for the evening DPC. Good evening.
Good evening, Expedition 69. A fresh plan for tomorrow is on board, but please do expect a few more changes overnight. And we do have a few additional topics from Houston when you're ready.
Hey, Jay. Hey, Jay, good evening. We are ready.
I wish I could take credit for Jay. This is Justin. We swapped up for today, but first topic up for Steve and the reported headset with a broken switch. We're curious where you ended up sewing it.
It is above the MWA.
Starboard side.
And it's above the MWA starboard side. It has a label on it. asking people to look at the indication on the ATU to make sure they're in the right position. I was able to get to each of those. Yeah, I loosened it.
Okay, we copy. Thank you.
Either way you turn.
Also for you, Steve, and your crew notes on the PAM Photo TV stow, we will schedule an activity for you tomorrow to stow this in the PMM starboard 4 location, as it will not be needed again until PAM 3.
All right, thank you very much.
All right, next up for Woody and the PFS mesh bag that we talked about earlier. That should be temp stowed at PMM starboard 4 rack front still. We'd like to confirm that it is just the mesh bag that is stowed there and not a CTV that contains the mesh bag. And that mesh bag can stay there on the rack front until its next use a couple of months from now.
Okay, we copy. Actually, it is still in that 2.0 CTV, but we can get it out, so it'll just be the mesh bag, and I will do that right after DPC.
All right, good plan. Thank you. And last up for Woody and your crew note on the SSC derail this morning, we're putting together a task list activity to do an audit and would like to confirm that the final location of the items you mentioned in the crew note, and if they ended up in node 2 starboard 6.
Negative. That SSC was redeployed to node 2, I think it's port 3 or 4, and the other items, the power cables and Ethernet cables, are just temp stowed for now.
Can we confirm they are temp stowed in the same location around port 3 and port 4 area?
Affirm.
We copy. That is all we have from Houston. Do you all have anything for us?
Hey Justin, nothing further. Was wondering though, SSC 7, can we move that back from the CASA to node 2?
You can go ahead and move that back.
Okay, thanks so much. Otherwise, nothing further from the crew. Thanks so much for the help today.
And thank you all. It was a busy day. It was great to work with you. Huntsville, Munich, and Scuba are standing by with no topics, and I will hand you over to Sergei Moscow.
Okay, sounds great. Huntsville, Munich,
I don't remember exactly where.
Good evening, and thank you so much for the
forward
support today.
5 or 6 left of LSG.
Thank you, thanks.
All right, welcome back to the airlock aboard the International Space Station. It's June 14th, getting ready for a spacewalk tomorrow, and we are pretty much all ready to go. We just completed our final tool config checks to make sure all our tools are ready for our spacewalk, and I thought I would just go through our tools and give a little bit of details on some of the things we use when we're outside. So on the front of our suits, we have what we call the mini workstation. The mini workstation is a place to put all our tools. It actually swings down. By swinging the mini workstation down out of the way, we can access things right on the front of the suit here. That includes our O2 actuator, which controls the pressure inside the suit. It allows us to access our mating location for our service and cooling umbilical, and also our controls for temperature inside the suit, and volume and display brightness. So occasionally during the EVA, you may see us swinging the mini workstation out of the way to access some of these controls. On my left side, I have something called a BRT, or a body restraint tether. The BRT can clip onto handrails and scoops outside the space station, and by tightening this collar, it actually becomes rigid. And we have these joints down here. There's a pitch joint and a yaw joint. And once we lock it out, this is a fairly rigid restraint. So we can control our body position by clipping onto structure. And this is good for things like driving bolts or getting our hands free to do tasks when we don't want our body orientation to change. We also use the BRT to carry around bags, and we have a little tether here ready to clip into bags to make sure that they stay attached. You may hear talk of something called a RET. RET stands for Retractable Extendable Tether. It's just a little tether on a reel, and it's got a hook on the end. This thing stays locked unless you depress it in just the right way to open it and clip it onto things. It also has a lock on the reel. This allows you to lock the RET out so that it's not pulling tension on things, because side loading can be really tricky when you're doing mechanical tasks outside, and sometimes we don't want the tension of the reel pulling back on whatever we're working on. On the other side we have a swing arm, and this is where we keep the PGT, or pistol grip tool. It's basically our space drill, and this thing lets us torque bolts. We can set it to clockwise or counterclockwise at different speeds, and then we can also set the torque. We have 14 settings for torque, alpha 1 through 7 and bravo 1 through 7, and that lets us set the place where this thing torques out and allows us to precisely control what we're torquing different fasteners to. Now the PGT, we can switch out sockets on it. We actually have a special RET with a pip pin on it, and what this pip pin lets us do, if we do a socket swap, is we put the pip pin in there, and that allows us to remove the socket and change it out for a different one. We have, this one's a 7/16 inch wobble socket, but we have many different socket sizes. Tomorrow we'll be using 7/16 and 5/8 inch sockets on our EVA. Stow the PGT back on the swing arm. Now actually here on the back side of my mini workstation I also have a trash bag. It's got these little bristles, so if we put something in there, hopefully it stays inside and doesn't come back out. I actually have staged in my trash bag a 5/8 inch socket, so I'm ready to quickly switch to this one when I need it instead of the 7/16 that's installed on my PGT. Also on the mini workstation we have this thing called the mini workstation end effector. This is a really useful quick body positioning device. We can clip this into something and it's on a spring-loaded retracting tether, and that can pull us in gently towards structure and just keep us positioned where we want to be if our hands are busy. Then the final thing I'll show is just our safety tethers. So on my left side here I have this safety tether reel, and the way this works is we will actually clip this in outside the space station. We'll clip it into a fixed location, and then as we translate with this reel, the reel sends out safety tether. It's actually just steel cable, and we move further and further away from our anchor location as we're translating around the space station. This one's 85 feet long, and we actually left two safety tethers, one for myself and one for Steve, outside the space station on our last spacewalk. So the first thing I'm going to do when I get out the door is I'm going to inspect the load alleviating strap on those safety tethers that we left outside, and then I'm going to hook up to them and create what we call a safety tether pack. And what that does is it doubles the length. So instead of 85 feet of length, we will have 170 feet of throw to get all the way out to the S6 location, the starboard 6 location on the space station. That's the furthest point starboard, and that's where we'll be installing solar arrays tomorrow. We also have, so that's our safety tether. That's what always keeps us tethered to a certain location. And then we also have these things called waist tethers. They also have the load alleviating strap. It's like what's called a screamer in climbing. And this waist tether is useful to just clip in for a local attachment point. If I want to get my hands free and do a task, I can clip in my waist tether. And that's it. Okay, this is pretty cool. It's July 3rd, And a couple weeks ago, we installed the new ISS solar arrays. When those arrays came up, 2 of them, they flew aboard something called the FSE, the Flight Support Equipment. And that's a big metal bracket that they mounted to that restrained them during their launch up here to the space station. And we have just jettisoned the flight support equipment. So it was on something called the POA, holding it on the truss of the space station. But just today, ground controllers used the Canadian robotic arm to grapple the FSE, remove it from the POA, and then we took it down below the space station and released it. And because it was just slightly nadir or below the space station, orbital mechanics tend to have it go forward of us and keep flying off in the direction of our velocity vector. So you can see the flight support equipment down below us, falling away and heading out ahead of the space station, and it will slowly decay in orbit over the next days and weeks, and eventually it will re-enter the Earth's atmosphere. And it's great to get rid of mass aboard the space station, because anytime we do a reboost, it's more efficient propellant-wise to have less mass up here. It also frees up grapple fixtures that we can use for other hardware. So the POA is now free to hold other equipment that we might want to use during other EVAs. All right, welcome to Node 3 aboard the International Space Station. This is not normally how this module looks. Normally, our toilet stall is right here. We've actually pulled that out of the way so that we can rotate this rack up. Now, this rack contains many of our systems for water reclamation. So that's all of the equipment that we use to convert urine into clean drinking water aboard the space station. And today, we've been working on swapping out some modules in this rack. We're actually going to be installing a new purge pump and separator assembly later this afternoon. This morning, what we did was we rotated the rack up and we started routing some power cables, as well as this separator vent hose, some of the plumbing that we're going to be hooking up later this afternoon. And we had to rotate the rack because these cables actually route all the way through the bottom of the rack, and they kind of poke out behind the rack. And we've been spending a lot of time down in the guts behind the rack. So I'll show you real quick. Back behind this rack, you see we have access to a lot of systems. And this is that same power cable we were just looking at. And so we have access to route it and get it nicely secured back here in the back. It's kind of cool back here. We don't often rotate these racks, but you can actually see right here the pressure shell of the International Space Station. So we are living inside of a cylindrically shaped, many cylindrically shaped modules. And this right here is the pressure shell that is holding 1 atmosphere of pressure inside the space station in here, and right outside this shell is the vacuum of space. Some other details you can see here. This wiring leads to these things we call shell heaters. So this shell heater is used to maintain the temperature of the shell and make sure that thermal contraction and expansion don't impact the structural integrity of the pressure shell. And so we're pretty careful when we come back here. Normally this is all protected by the racks, but we're careful not to damage this delicate wiring and these shell heaters. And so this afternoon, Sultan and I are going to be finishing up installing that purge pump separator assembly, and then we will rotate the rack back and get everything closed up and back to normal. All right, welcome aboard the International Space Station. This is Node 2. That way is forward, and what we mean by forward is that is the direction of our velocity vector. And we are in a very special time right now. We are actually in the middle of a reboost. So the thrusters on the aft end of the space station are thrusting right now in the direction of our velocity vector to speed us up. So normally on the space station we are completely weightless, no acceleration at all. But right now the space station is being accelerated that way. And therefore, if I get really still and let go, we'll actually see the acceleration happening in the form of me starting to accelerate backwards. And the longer we wait, the faster I will be moving. It's an actual acceleration. And I can show you this is definitely real because I will actually give myself an ever so slight forward speed. All right, now I think I'm moving forward and I'm just gonna wait, and eventually the acceleration's gonna null out my forward speed and I'll start moving backwards. It looks like I gave myself a little bit of downward speed as well. Nothing will change that. But here we go, now I'm starting to move backwards. So we use these reboosts to periodically raise the perigee, or the lowest point of our orbit, and we also tend to time them if we have any concerns about conjunction, so orbital debris that could be impacting the space station. We time the reboosts to move this trajectory of the space station out of the way of that orbital debris. All right, see it. All right, welcome aboard the GEM, the Japanese Experiment Module aboard the International Space Station. Today, I'm going to be doing an activity with our Astrobee robots. So we're just getting started. I'm actually going to call the ground here soon, check in about exactly what we're doing today. I know we're doing some gesture recognition work and testing out that software. And we will get going here. Should be a good day. Huntsville Station on 2 for Astrobee. Penny, thank you. I copy, switching to 3. Huntsville Station on 3. Good afternoon, Eric.
Hey, Woody, great to be with you. How do you read me right now?
Hey, Eric, great to be with you. I have you loud and clear.
Today's activity is in preparation for a student event that's going to be held on next week, and we're going to be running ops with you again. So today is going to be a dry run for that event. This is a project called Zero Robotics. Are you familiar with Zero Robotics?
Yes, I've heard a lot about Zero Robotics. I think it's just awesome that we're going to have students involved in writing code that's running up here on the space station. I'm really excited for it.
Today, what we're going to be doing is, for each run, you're going to be performing 3 hand gestures in front of the Astrobee, in front of the science camera. And you're going to want to be about 30 to 50 centimeters with the hands in front of that science camera. That's the sweet spot. I would say closer to 50 centimeters than 30, but you'll figure it out as we go. We'll be back with you. We are ready for cruise step 2.2 to undock Bumble and place in the base 6 area, and then we'll fire up the impellers.
Eric, I copy, and work. All right. Pull it off the dock here. And the home position is right about here. Just let it go there.
Woody, that was a great first run. We're very excited here on the ground. The next run is going to be numbers 3, 4, 5. Are ready when you are.
Eric, I copy. I'm ready for 3, 4, 5.
Stand by for flashlight. Woody, that was a successful run. We are ready for the next run. The numbers will be 3, 5, 9.
Eric, I copy. 3, 5, 9.
Stand by for flashlight.
All right, so after I put in the gesture, Astrobee does some position and orientation changes in response to the numbers that were displayed in front of the camera. All right.
We're ready for 469 again.
Eric, I copy. Standing by for 469.
And that's Bravo.
So the last run, the classifier misidentified 469 as 464. So we're going to give them this run again and hopefully provide some more training data. So I'm waiting for this little flashlight on the front. There it is. That's a 4. That's a 6. And that's a 9. Now we'll get out of the way. See what they got. You can see a little bit of detail. These are the vents. They're blowing out air all the time, but the little louvers in there open and close.
Rudy, this was another interesting one. We visually saw 469, so you're doing good there. The robot saw 465 this time, so very interesting. Stand by for a decision to rerun again, but again, part of the data.
Yeah, that's really interesting, Eric. I'll be standing by. All right, so it sounds like 9s are hard to classify. What I don't know is whether the team on the ground is building this classifier for these gestures and providing it to the students as a module or software package that they can use, or whether this is the task the students have, is to classify what gestures the robot is seeing. So it'll be interesting. So you can see some detail here on the Astro B. There's fans running, blowing air through the vehicle all the time, and then there are these little vents with little louvers inside that control, open and close to control how much airflow is coming out. And there are, looks like 2 on each side. So 2 on the bottom, 2 on this back face, 2 on each side, and so a total of 12. That gives you control authority for both position and orientation in 3-dimensional space. And then on both sides there's a sort of whole suite of sensors. The side that I'm avoiding right now is what it's using for navigation. There's a nav camera up there, and then there's also something called the science camera. That's what I've been doing these gestures into. Back here on the back we have a dock cam and a perch cam. This is the side of the Astro B that docks to the charging station, and it can do that autonomously. And then there's also a perching arm that can be configured onto the Astro B, and it can do things like perch onto handrails. So it's a pretty cool vehicle, and it's a great platform for things like student competitions. Just a really versatile, reliable platform for doing cool stuff up here. All right, hello. So it's the evening of August 3rd. A couple nights ago, the Cygnus spacecraft, it's an uncrewed cargo vehicle, launched out of Virginia, and it's actually up here in low Earth orbit with us, chasing us down right now. And tomorrow morning, Frank Rubio and I are going to be assigned to fly the space station robotic arm in to grapple the vehicle, and then the robotic arm will berth the Cygnus vehicle to the Node 1 Nadir hatch, which is right behind me. So we'll have a lot of new supplies tomorrow morning, as long as we can successfully grab that vehicle with the robotic arm. So this is one of 2 robotic workstations we have on the space station. The other one is actually in the cupola. We have a great view from the cupola, and that's actually where we'll do the operations tomorrow morning, looking right outside as we work. But this is our backup RWS, or robotics workstation. We actually have 2 power strings on the robotic arm, and we have these 2 workstations, and we can switch back and forth between these if we have an issue on the other one. Here at the robotic workstation we have 3 cameras. They're not quite set up yet for tomorrow's capture, but we typically have a center camera looking right at the target that we're moving the arm into, and then we have 2 side cameras that can give us a bigger overall situational awareness view of what the arm is doing. And then we have the hand controllers here. So on the left is the translational hand controller, 3 axes, so up, down, left, right, and in, out. It just moves the arm in, out, left, right, and up, down. And then on the right, we have the rotational hand controller. We can pitch forward and back, roll left and right, and yaw left and right. And that's changing the orientation of the end effector of the robotic arm. And then we have our display and control panel here with a bunch of switches that we use as we get into some of the operations. We can move cameras through that and deal with some backup modes for actually capturing the vehicle. Now, behind the robotics workstation, we have a workstation that we use for practice. This has an acronym that's actually ROBOT, but it's really our robotic trainer station. It's a similar setup. We've reproduced those 3 monitors up here. The center one is the one that we're really focused on as we drive into the vehicle, and then bigger situational awareness views on the outside. And down here we have some of the PCS or space station computer pages that we typically have up during these operations where we can issue commands to the ISS. And so tomorrow Frank and I will go through a lot of operations to get the space station ready, and then we will get the go eventually from mission control telling us that we are go for approach to capture. We'll set up actually the space station attitude control systems, get changed right before we do the capture, and then we will get hands-on hand controllers and start in. And so at this training station, we do 2-meter runs. So this is actually pretty far in on the approach. And what I'm going to be doing, the fixture that the arm is grabbing onto is right here. It's a pin with 3 cams sticking out from it. And the arm comes in to grab it. And as it does that, up here above, there is a target. And so my goal is to fly in and right up to that target to a certain depth. And I have some target markers here that help me assess how deep I'm going and also assess alignment to the target. The big picture, we want these center green crosshairs on that target, and you'll see a small pin inside a small circle on that target. That pin is what tells me my orientation relative to that target, and I want it to be centered. I'm going to go ahead and get this going. So we'll unfreeze dynamics.
And free drift, go for approach.
And the vehicle is now simulated in free drift. So I start by getting a feel for what the rates are on the vehicle, mostly the translational rates. I'm at the same time watching what's happening with that pin over time to see if I'm going to need any orientation corrections. I'm trying to let my oscillations damp out from moving the arm. I see we're going to need a little bit of roll, so I'm going to start feeding that in gently. And I think we need a little bit of pitch up, so I'll start feeding that in. And with those open loop inputs in, I will start forward toward the vehicle. And now it's just a game of detecting errors and putting in very small changes to correct them. So I see I need to continue a little more roll, and I do see I need to be a little more aggressive on pitch. Now when you put in a pitch input with your right hand, of course that makes the target go up in the view, so you need a corresponding translational down command on the z-axis with your left hand. So you kind of get the feel for coupling those together eventually. And my control inputs are like super small, and that's just to avoid any oscillation in the arm.
1.5 meters.
This is looking pretty good, pretty stable.
Two pins.
2 pins, we're going to continue.
One pin.
1 pin, continue.
Over the pin.
Over the pin, looking good. Coming up into the capture envelope, trigger. hands off the hands controllers and the snares inside the latching end effector, grab the pin in this simulation, and then the end effector begins the process of slowly reeling tension back on the carriage inside it, and that's what ultimately achieves a hard connection between the robotic arm and our lovely new Cygnus vehicle. So this is great training, and that's probably one of the last runs I'll do. I'm going to get a good night's sleep tonight and get up tomorrow morning ready to work with Frank to get ourselves a Cygnus. See ya! Alright, I thought I'd show you a feature we have in the Japanese Experiment Module, or GEM, and that is the GEM airlock. And this airlock allows us to send small items from inside the space station to the outside. In fact, let me show you. So here's one hatch of the GEM airlock, and the other one leads to space. It happens to be located right next to a window here in the GEM, which I can open. Well, I can open a shutter on the outside. And right out here is space. Directly outside the GEM is the JEF, or Japanese Exposed Facility. There's lots of interesting payloads out there, and the other thing you see right in the center of the screen right now is the end of the GEM arm. That is a small robotic arm that can move equipment around on the JEF. And so the way this works is that we can send equipment out through this airlock here in the GEM. We prepare it inside. We put it on a slide table inside the airlock. It slides into the airlock itself. We close the hatches. We depress the airlock down to vacuum, and then the hatch on the other side of this airlock leading out to space opens, and the GEM robotic arm can extract the payload, and then the main space station robotic arm, our Canadarm2, can actually do a handoff with the GEM robotic arm and take control of the payload. So most recently we used this capability to deploy some small satellites, and what I'm doing today is I'm going to open up this hatch here and pull all of the equipment that was used to launch those satellites, the satellite launcher, and I'm just going to deconfigure it, get it off of the slide table here in the airlock so that we can have the airlock ready for other activities. Hatch lid able to unlatched.
CDs except for the external SDL for 5 CDs.
Ah, the smell of space. This volume was most recently at vacuum and then repressurized. But all this equipment in here was recently at vacuum. And it creates this interesting smell. The other time we smell this is when we come in from a EVA or spacewalk. Some people say it smells like burnt chicken. I think it smells just kind of metallic, maybe like after a lightning storm, but a really, really strong version of that. It dissipates after some time, but you really smell it when you first access any equipment that was at vacuum. Alright, it's time to extend the slide table. This is a cool mechanism. It automatically extends. I've done all the command setup, and I'm one switch throw away from extending the slide table. Here we go. Now we've got access to do work on the satellite deployer. Alright, before I get started removing all this hardware, I'll take you on a quick tour. So this is our launcher that deploys these small satellites. The satellites come out this way, toward you. There's actually two launchers, this one and this one. And this unit here is actually on a spring. So inside that rectangular tube that can hold a good many of those small satellites, there's a spring in the back, and that provides the force to launch the satellites. To hold them inside, there's this little lock. It's popped open now since it already deployed the satellites, but when it's holding them in, it's held in place by this small cam that can rotate, And a simple command from ground controllers allows that cam to rotate out of the way, and that's what actually launches the satellites. Now back here, you see everything's covered by this MLI, or multi-layer insulation. Underneath the MLI here, we have an electronics box and some wiring to control those mechanisms in the front. And then back here toward the back of the multi-purpose experiment platform is this grapple fixture. And this grapple fixture is what allows the robotic arm to grapple on and manipulate this hardware into a good location to launch the satellites. This experiment platform is currently on the GEM slide table, but that can actually be released. So that's another one of the commands that ground controllers send, is once the robotic arm has grappled on to the experiment platform, it can be released from the slide table and manipulated in space. All right, we got that satellite deployer removed from the slide table. And now it's just that MPEP, the multi-purpose experiment platform, remaining, and I'm going to retract it back into the GEM airlock and get the hatch closed back up. Alright, I'm done with my work at the GEM airlock. I do have one little piece of trash here. I put away all my other tools and equipment, but the last thing I need to do is throw this piece of trash away. It goes to a specific, what we call JSB or jettison stowage bag. These are blue bags that are basically trash bags up here. And we have a specific one for hardware trash. So I'm going to take this from the GEM here over to the PMM to throw it away, and I figured it's a good chance for a quick tour. So we're in the GEM right now, facing station port, and we're just going to fly on over to the PMM. Come with me. We're going to make the right turn here into node 2. Now we're facing station aft. Coming through the US lab. And into node 1. We'll make another right turn facing station port. This is node 3. Got Sultan doing some exercise here. We're going to pass on by into the PMM. And back here, now going station forward at the back end of the PMM, we have all these trash bags. Get flipped around here. And one of these is for hardware. So I'm going to find it. Here it is. And this is where I will throw away my small part. Hope you enjoyed the overview of GEM airlock ops and found it interesting, and have a great day. Hello. All right. Thought we'd give a quick overview of some of the exercise we do in space. Other than sleeping, exercise is probably the item we spend the most time on up here. We do about 2 hours and 15 minutes of exercise every day, about 1 hour and 15 of lifting weights, or we call it resistance exercise, and then the other hour is cardio. So how would you lift weights in space when everything's weightless? The engineers at NASA came up with a really cool solution. So this machine is called ARED, which stands for our Advanced Resistive Exercise Device. And the fundamental operating principle uses a pair of vacuum cylinders. So up here, we have these 2 large cylinders, and inside these cylinders is a vacuum. So pulling open a cylinder under vacuum creates a lot of force. So on these 2 arms here, when you pull down on those arms, that creates a lot of force. These are pulling upward. And this whole machine is built around these 2 pivots right here. So as these arms pull up right here, around the pivot, the rest of the device, including this arm and the bar that I lift on, are pulled downward. That pulls up, this comes down. By changing the location of these arms relative to this pivot point, which I do through this crank, I can dial in different weights and change the distance at which those vacuum cylinders pull, change their lever arm. And so through that, we're able to vary the resistance that we feel on the arm. So this machine allows us to do a wide range of different exercises. Today I've started off with several sets of single leg squats. We have a team on the ground of what we call ACERs. Those are our astronaut strength conditioning and rehabilitation folks. And our ACERs prescribe individually for us a set of exercises that gets us ready, kind of maintains hopefully our muscle mass and bone density up here, and gets us ready, in my case, to come back. In a few weeks I'll be returning to Earth, so I want to be as strong as I can be for that. So I'm actually on my last set here of single leg squats. So the way this works, I need to update the computer for the last set, and then just get in the ready position. So normally I'm completely weightless. There's really no way to feel weights or feel like I'm standing with any force on the ground. But on ARED, I come in under the bar and I lift it up off the stops. So now I'm holding the weight, and it feels a lot like lifting weights, squatting on Earth. I feel force through my feet. I feel the weight of the bar on my shoulders, and now I can get into my reps. In this case, I'm doing 10 reps each leg, so I'm going to switch here at 10 reps. Do another 10. And then we just lean forward, and that allows the weight to rack. And I'm back to being weightless. The other final cool thing I'll show, this whole machine, obviously we do a lot of motion on ARED, and so the entire device is isolated from the structure around it through a set of springs and dampers. So you can see I can just move ARED around here, and through 3 different axes, well, I should say 2 axes of translation, so up, down, and in, out, it's isolated, and then it also has a final axis of rotation. It can pitch here. So 3 axes of isolation, and there's dampers in there, so it'll slowly return to center over time, and that just allows us to create motions here without imparting them into the structure of the space station. See it. Hello. All right, I'll show you the second of 3 exercise machines we have. This is called CVIS. This is our bike. It's pretty simple. One of 2 cardio options that we have. And we spend about half an hour on CVIS when we do exercise here. It's just a bike. One of the first things you notice is there's no seat. I'm weightless, so I can just sit here pedaling against the resistance. I've got clip-in shoes, so I can push down, pull up. Now you find, just because your leg's a little stronger pushing than pulling, you find that grabbing these handrails, particularly when the wattage gets high, is useful. As I push down a little harder, I end up pulling up with my arms. The whole bike is situated on a vibration isolation system. Famously, way back in the day, there were some issues with these vibration isolators and the damping, and so I believe Don Pettit's socks are in here. I can still feel them. There's a balled up sock in each of these 4 vibration isolators. The computer here allows us to run different programs, adjust wattage, and it's a constant wattage. So when we're pedaling, if you increase the cadence, then you can actually feel the resistance goes down. So I feel the system accommodating for my increased cadence by lowering the resistance, or I can slow down my cadence, and as I do that, the system kicks in, and to maintain the same wattage, I feel it upping the resistance. And we pedal about 75 RPM, something like that. We also do our VO2 max testing here, so we have a mask and we have a whole system with a bunch of plumbing to run VO2 max tests up here. That's a little brutal. And that's about it. So spend a lot of time here cycling away, getting our cardio in. All right, see ya. Howdy. Alright, I put it in cool down mode. So this is our treadmill. We call it T2. The second of two cardio options we have for workouts up here. And it's just a treadmill. Of course we're weightless. So how does a treadmill work? Well, we bungee ourselves to the platform and get about, I have a little over 100 pounds of load right now down through this suspension system. And it's surprising you can walk or run a lot like being on a treadmill on Earth. Now, I have less load on my feet than my weight. I weigh about 185 pounds, so I'm much less load than running on Earth. But I do feel like I'm wearing a 100-pound backpack here, right? It is, this suspension system is just like carrying a heavy backpack hiking. You have some load on your hips, and you distribute that with load on your shoulders. I'll go ahead and pause here, show a little more. So, the treadmill's mounted on the wall. We've got our feet on the wall, facing the floor as we run. And it's pretty cool when you get on here and you've been weightless all day, no loading through your skeletal system. I notice the first few strides, I have this funny kind of nerve sensation in my feet. It feels really amazing to get some pressure on my feet and feel that sensation of loading up my feet again. And the whole system is mounted on a vibration isolation system. We've got these dampers and little snubbers in these rubber cups down here that allow some freedom of motion as we run, and then also keep the platform constrained so that it doesn't impart too much load into the structure of the space station. We do have some constraints sometimes. For example, if we're doing a reboost or we have vehicles docking, we can't use the treadmill just because of that loading into structure. We wear a heart rate monitor. This is the receiver for the heart rate monitor. I usually have my podcast up here, maybe something to drink. And this is one of my favorite systems for exercising. So we call it T2. It's also famously down here, you can see there was an online naming competition, and this is the Colbert. So after Stephen Colbert's show, his fans decided to name this treadmill the Colbert, and we, NASA, came up with the acronym. So I guess Colbert stands for Combined Operational Load-Bearing External Resistance Treadmill. And it sure is a great place to work out. Thanks, Sultan.